Welcome back, Rock the JVM fans, to another video. I'm Daniel, and in this video we're going to explore Scala 3 with some of the new types that were embedded into the language and into the standard API. Now, this video will assume that you know some Scala fundamentals, and because we're exploring Scala 3 in September 2020, when Scala 3 is not even officially released, I'm going to assume that you know some Scala 2 fundamentals because we're going to write some Scala code. Scala 3 hasn't really changed the fundamentals of the language, but it has embedded a number of breaking changes into the language. And this video will also assume that you have a recent version of IntelliJ IDEA. I use 2020 version 2. You can use an equivalent development environment like Metals or another development environment of your choice that will support Dotty. We are recording this in September 2020 when Scala 3 is not even officially released. It's under the codename experimental version called Dotty, and this will become Scala 3 officially late 2020. As always, I'll recommend that you code with me in this video, and whenever you need to refresh your memory about these new concepts in Scala 3, just refer back to this video or to the written version at rockthejvm.com/blog with a link in the description. So with that said, let's get back to our development environment, and here I have IntelliJ IDEA version 2020.2. All right, and this version has support for Dotty. Dotty is the experimental new language that will become Scala 3. And if you want to create a Scala project with support for Dotty, you would go to File, New Project, and you would click on Scala and then click over here, Dotty. And after you click Next, you would carry on with the rest of the wizard. You would name your project My Scala Project or something along these lines, and then you would put it into the folder of your choice. All right, I'm going to hit cancel because I already have a plain Scala project already created with Dotty support. And I've created a new object here under source main Scala. I've created a small package here called blog, and I'm going to explore some of the features in Scala 3. I've created an object so that we might test some stuff with a main method. So I typed in main, and IntelliJ IDEA is still smart enough to autocomplete this method signature for me. So let's explore some of the new stuff that's coming in Scala 3 in terms of new types. And the first thing that I'm going to talk about is literal types. Now, this feature was technically introduced in Scala 2.13, but we'll explore it here in the context of types that we're going to talk about next in this video. Now, in short, Scala is now able to treat literal values as singletons of their own types. Now, if you remember the type level programming mini-series, which we also have on YouTube, and I really recommend you watch, it's pretty interesting, we needed to define each number as its own type, but now Scala can do this by default, and the catch is that you'll now have to declare your types explicitly. Let me give some examples. So I'm going to define a val, let's call this a number, and on the right hand side I'm going to make it 3 or something like that. Now the compiler will automatically infer, obviously, the type of a number, which is going to be int based on the right hand side, the value 3. But I can also define a value, let's call this 3, whose type is not int but rather the type 3. So I've defined the type 3, and on the right hand side we have the only value of that type, the number 3. So notice that if you don't specify the type of your value, the compiler will infer the type based on the right-hand side as it did before with the type integer. But if you specify the literal type yourself, then the compiler will automatically build a new type behind the scenes based on what you declared. And any literal can become its own type, and it will be a subtype of its normal type. For example, the subtype 3 will be a subtype of int. So it's as if the compiler could create a class or some sort of type that is a subtype of int. Right. Now, if you have a literal type, you can use it to interact with some kind of method, for example, in your APIs. So I'm going to define a method, let's call this passNumber, which receives an argument, let's call this n of type int, and just prints it to the console. I don't really care what it does. All right. Now, given the fact that this method receives an int, I can obviously do passNumber with, say, 45 because it's an int, but I can pass a value of a literal type, which is a subtype of int. So I'm going to say pass number with 3. And this also compiles. Okay, so this is also fine. However, the converse is not true. So if you wanted to somehow restrict your types to a literal type, then a plain number will not do. So if I define a method called passStrict, for example, and I can define a number which is of type 3, look at that, and I print it to the console, I don't really care what the implementation is, I can passStrict with my number 3, because I've defined it with the correct type. But if I do passStrict with, let's say, 45, then this is a compiler error because 45 is an int. I require the number 3. All right, so this is not okay. But this is pretty common sense because you are defining a method of a more restrictive type and you want to use an argument of a more general type, and normally this will not compile. Now, literal types can be defined for other numerical types, for example, doubles. So if I define a value called pi of type 3.14, so look at the type. The type is 3.14, and on the right-hand side, obviously, I need to match that. This is perfectly applicable. So you can define a number as its own type, regardless of whether it's an int or a double. You can also define the truth, which is of type true. And obviously, on the right-hand side, you have to conform to that. Or you can define strings as their own type. So I'm going to define, let's call this my favorite language, which is of type Scala, for example. And on the right-hand side, obviously, we'd have conform. So notice that strings can also be their own literal type. Now, a side note, string is a reference type, unlike the other types that we worked with, but the string interning mechanism, which happens under the hood of the JVM, takes care to store these strings as if they were simple primitive values. All right. Good. Let's move on. So why are literal types useful at all? Literal types are used to enforce compile time checks to your definitions so that you don't go reckless with your code. So if you know for sure that a method such as passStrict can only support the number 3, then you have no choice but to supply a number that is applicable to the type 3 here. So if I define, let's call this do something with your life, and assume this method takes an argument that I'm going to call meaning, which is the meaning of life, and I'm going to pass option 42 here, and on the right hand side I'm going to simply say meaning for each print line. I don't care about the implementation, but given the signature of this method will only take either sum 42, which is an option 42, or none, and nothing in between. It will not accept option 43 or option 0 or option of any other kind. So it's often a good idea to restrict your type declarations to literal types when you are certain that your particular value, in our case 42, is critical for your application logic. So in this way, you will avoid the errors of passing invalid values. All right. So prior to literal types, even though you are certain to only need the value 42, you would use option int here. But any other value other than 42 is an error, and it might cause some issues if you fail to treat anything but your critical case. But now with literal types, the compiler forces you to do that before the code even runs. All right. So this is one of the uses of literal types. The second thing that I'm going to talk about is union types. And this is a completely new addition to Scala 3. So it allows you to use a combined type, either A or B, in the same declaration. However, this has nothing to do with the either monadic type. So this is not equal to the either type, which is already embedded into the Scala standard library. So a union type looks like this. I'm going to define, let's call this ambivalent method, whose argument is a string or an int, written like this, string bar int. And if you want to treat both cases, you can say argmatch, and you can do a proper pattern matching here. So in case you get something which is a string, then I'm going to print line a string, and I'm going to inject arg, and in case you get something which is an int, I'm going to do something else like print line. Let's call this an int, and I'm going to inject argument again. Now, this ambivalent method happily receives either an int argument or a string argument. This was not possible in the prior versions of Scala. So we can use this method as ambivalent method with 42 or ambivalent method with the string Scala. So this is perfectly applicable with both kinds of arguments. Now, the caveat of having a union type in a method or a function is that in order to use these types properly, for example, use their methods like the length of a string or the addition of an int, you have to pattern match the union typed value against the possible types, much like we did here. Now, I mentioned we would discuss literal values earlier. In the context of Scala 3, even though literal types were introduced in Scala 2.13, because in conjunction with union types, these literal types unlock a very nice piece of functionality. Languages like TypeScript have had what I'm going to show you for years, and it's really nice that we can have the equivalent in Scala. So in my previous experience, I also dealt with TypeScript and I wrote a bunch of front-end code, and we used to have some types that looked like this: type error or, and this had a type argument t, has t or a string like error. And this is now possible in Scala. This puts some restraints on what you can do with your value. So for example, if you had an API method that looked like def handle resource, which had a file, for example, as an error or file, and we would import file from Java IO, and let's assume this thing returns unit and I don't know, your code here. I'm just going to return the unit value. Now, if you wanted to use this method, you cannot access the API of your argument here, of the file, unless you treat the error case as well. So this prevents you from being very reckless in your code and forces you to treat unwanted values like error properly. And the best part, everything happens at compile time. All right. So let me discuss one more thing about union types. They are not inferred automatically by the compiler if an expression can return multiple types. In other words, the compiler will still compute the lowest common ancestor type by way of inheritance. Let me give an example. Let me define a val, let's call this string or int, as if 43 bigger than 0, then I'm going to return a string, else I'm going to return the value 43. Now, this is a perfectly valid expression in Scala, and on one branch it returns a string, and on the other branch it returns an int. Now, the inferred type by the compiler is any. This is the lowest common ancestor between a string and an int, and this is what the compiler will give you. But you can use a union type explicitly, and the compiler will be happy if you do. So if you wanted to restrict your type, you can say a string or int of type string bar int, so string or int, and I can pass the same expression here, and the compiler will be happy with that. So I hope it makes sense. Union types are a welcome addition to the Scala language, and we will see some pretty expressive APIs with these. And the third thing that I'm going to talk about in this video is, by way of symmetry, intersection types. So we now have intersection types in Scala 3 now, and while you can think of union types as A or B, intersection types means A and B, so both A and B. So here's an example. Let me define a trait called camera and a trait called phone. And in camera, I'm going to add a method like take photo, and this should print line something like snap or something like that. And in phone, I'm going to add another method, let's say make a call. And I'm going to print something else like ring or something like this. Good. Now, having these two wildly distinct types, I can define a method that's called, for example, use smart device. And I can pass an argument that is both a camera and a phone. So I'm going to say camera and with the ampersand phone. And inside, because this argument adheres to both the camera and the phone types, I can use both their APIs. I'm going to say sp take photo. At the moment of this recording, IntelliJ is pretty bad at auto-completion, but I'm pretty sure it will be up to speed by the time Scala 3 is out. And I'm going to say sp.makeCall. And this code is perfectly compilable. So inside this method, the compiler guarantees that the argument will adhere to both camera and phone APIs, so you can use both methods inside. And this intersection type will also act as a type restriction, so we need to mix in both these traits if we are to use an actual instance in an actual call of this method. So I'm going to define, for example, a class. Let's call this smartphone, which extends camera with phone. And because I've mixed in both traits in my type, I can pass an instance of this smartphone to this API. So I'm going to say use smart device with new smartphone. And this is perfectly fine. All right, so I hope this makes sense. Naturally, an intersection type will be a subtype of both of these types involved. Now, some interesting questions. An interesting question that might come up is, what if the two types, like camera and phone, share the same method definition? Like have a method, let's call this use, that returns unit and takes no arguments. So I'm going to simply call sp.use. And also imagine that I don't have access to the class smartphone. What would happen? Is this code compilable or not? As you can see from the screen, this code is perfectly compilable. And if I go to build and say recompile, the compiler will not have any issues with my code. Even though I have a camera and a phone mixed in, I can have access to the same use method. Now the question is, which method am I going to call? Now, that would be an interesting question, but it's also the wrong question because the compiler doesn't actually have to care about which method will actually be implemented by who's ever going to call this method. It's my job as a programmer to supply a type that adheres to both camera and a phone and have a single use method that takes no arguments and returns units. So if I have my class smartphone that extends camera and phone, now I have to deal with a compiler error that the use method is conflicting in the traits that I'm mixing in. And it's my job to fix that. So I'm going to override use and I'm going to print line smart. And once I do that, then the smartphone will satisfy both the contracts of camera and phone because it will have a single use method taking no arguments and returning unit, and it also solves the conflict. And if I uncomment the call of use smart device, then it will also pass the compiler checks because this intersection type will only act as a restriction. The compiler doesn't actually care how the actual type is going to be implemented as long as I fix the prior compiler errors, which we did. Now, given the conflicting members here and the famous diamond problem that is present in languages with inheritance and with multiple inheritance in particular, we are going to address the exact ways Scala solves this problem and the diamond problem with trait linearization, but that is a subject for another video. So that was an interesting question with intersection types if both have a similar API. Now, another interesting question is, what if the two types share a method signature except the returned types? So assume we have the following modules. I'm going to define a trait. I'm going to call this host config, and a trait, let's call this host controller. Assuming we have a networking application or some kind of allocator of network resources, and I'm defining a method called get, which returns an option of host config. And I'm going to define another module. I'm going to call this port config, and a trait port controller, and with a method called get with no arguments and no parentheses that returns an option of port config. Right, so two very similar modules. So we have two similar APIs, the get method taking no parentheses, no arguments, and returning an option of a different kind. Now, assume we want to mix them in our main resource allocation server or something like that. I'm going to define a method get configs, and this receives a controller. that is both a host controller and a port controller. And on the right hand side of equals, I'm going to say controller.get. Now, the first question, does this code even compile? And the answer is that it does. So if I hit recompile, the compiler will be perfectly happy with my code because the get method here with no parentheses and no arguments is common between these two types, so we should be able to use it on the right-hand side. Now, the second question is, what type does this get method actually return? What type does this big getConfigs method actually return? Now, this is a tricky question because the argument is of type host controller and port controller. Any real type that can extend both host controller and port controller must implement this get method such that it returns both an option of host config and an option of port config. All right. So the only solution is to make this get method return an option of port config and an option of host config. So the type here is going to be option of host config and option of port config. And this is perfectly valid to the compiler. All right. Now, does this intersection type play well with variants because option is a covariant type? And the answer is yes, it does. Because option is covariant, it means that the subtyping between options matches the subtyping between generic types. So in other words, two options chained with an intersection type is the same as an option of an intersection type like this. So an option of host config and an option of port config is the same as a single option containing an intersection type of both. And given this, the code still compiles. So if I hit recompile, the Dotty compiler is still happy with my code. Now, this is a more tricky concept because it also involves variants, but this is sound with respect to Scala's type system. Alright, so in this video we explored some of the new types that the Scala 3 language brings to the table. Intersection types, union types, and literal types combined with the two. And given these, we are probably going to see much more powerful and expressive APIs real soon once Scala 3 is out. So let me know if you like this video, and I will create more videos on Scala 3. And if you like this video, go ahead and click the like button for me, and subscribe to the Rock the JVM channel for more videos like this. Obviously, I'm dying for feedback, so please leave yours in the comments. I read every single one, and go ahead and follow us on Twitter and LinkedIn for fresh updates on upcoming material. And finally, check out the Rock the JVM website. We have tons of material like this, including the written versions of all the videos on the channel. Until next time, I'm Daniel, signing off.